Before we address the behavior of the same solution at large negative x, for pedagogical reasons, it's more instructive to investigate the asymptotics of the solution given by the contour C1 at large positive x. So here is the solution in question. Of course it has the identical form, but due to the different placement of the contour, it will have completely different asymptotic behavior. It may be already seen from the position of the saddle. The contour is between the branch cuts, but the saddle is to the left of the left branch cut. The steepest descent direction is unchanged. The branch cut, though, obstructs the deformation of the contour towards the steepest descent line. To help you understand better what is going on, let me show you some 3D visualization. Here is the plot of the real part of the exponent function. Pay attention to the mesh. It consists of two families of curves. The first family are the level lines of the surface that you see. The second family is the steepest descent or stationary phase curves. The white curve represents the initial placement of the contour. The green dot marks the position of the saddle. The red lines and red dots are the branch cuts and branch points. As you see, there are two stationary phase curves crossing at the saddle at 90 degrees angle, as it should. The first one is the steepest descent path, and the second one is the steepest ascent path. The latter points directly at the branch point. Now, the very ideology of the steepest descent method assumes that we should move the contour in such a way that it occupies the lowest position on the relief of the real part of the exponent function. Here you clearly see that the contour should be moved leftwards. And here we go. However, as we move the contour in the direction of a saddle, it has to cross the branch point and the branch cut as well. The branch point is a singularity which can't be crossed, and the contour should be moved around it. However, as you see, if we want the contour to occupy the lowest position, it has to cross the branch cut. We'll return to this in a second, but for now, let me just point out that as drawn, the contour is placed along the stationary curves only. First, it arrives in the saddle along the steepest descent line, then it glides along the steepest descent line to the branch point, then it returns along the same line and finally leaves the saddle in the steepest descent direction again. To understand what is happening with the contour as it approaches the branch cut, let us have a quick look at the Riemann surface of the pre-exponential function. First of all, it's a square root, so it's comprised of two sheets. The contour is initially placed on the brown one. Let's call it the first one. As usual, the expansion of the Riemann surface into Riemann sheets allow us to forget about the branch cuts. In fact, now the branch cut is merely a segment which connects the two Riemann sheets. So when the contour starts circumventing the branch point, part of it, the upper half, simply slips onto the other Riemann sheet, the orange one. And here is the final geometry of the contour. Now it's spread between two Riemann sheets. The lower part stays on the initial sheet, while the upper part is on another Riemann sheet. We kind of encountered a similar situation when we discussed the saddle point approximation, and the optimal deformation of the contour contained the contribution from the pole and the saddle. Back then, the contribution of the horizontal forward and backward paths cancelled. Here, the respective parts of the contour belong to different Riemann sheets, so they won't cancel. That's the difference with the previous case. In fact, the simultaneous account of the saddle and branch point contribution may present quite a task. But here, fortunately, the branch point occupies the elevated position on the relief of the real part of the exponent function with respect to the saddle point. That means that the branch point gives the leading contribution. You see that the configuration of the contour near the branch point is a typical Hankel type curve, so we will basically use Watson's lemma to compute it. To understand in detail how to deal with this different Riemann sheet stuff, let's do the details. So we are interested in the vicinity of the branch point. Hence, we expand the exponent near the t equals to -1. we have the following change of simple algebra. As usual, the convergence regions is S of the order of 1 over x. So in the region when the integral accumulates its value, we have x minus 1 times s is of the order of 1 minus 1 over s. And we discard 1 comparing to x in 1 minus x factor. And of course, s squared over 2 is of the order of 1 over x squared and can be omitted as well. Thus, we have the following approximate expression for our exponent. And the expression for the asymptotics now reads, where, just a reminder, the g function is our pre-exponential. Now, let's figure out briefly how to tackle this multi-value g of t on the lower and the upper bank of the contour. As you remember, g of t defined to be positive for large positive values of t. So let's track down the change of the arguments of its constituents. When we go from the left real semi-axis to the lower bank of the contour, the change of the argument of the t minus 1 number is minus pi. The same is obviously true for t plus 1. So the total change of t squared minus 1 is minus 2 pi. When we make a square root, we end up with minus pi. As a result, g of t function will have the opposite sign on the lower bank. Now we expand it near t is equal to minus 1 point and obtain. A similar procedure should be performed for the upper bank. As you see from the picture, the t minus 1 change of the argument is as before negative pi. But the t plus 1 change is pi, however. As a result, the total argument of t squared minus 1 stays unchanged. So now g of t function at the upper bank preserves its positive sign, and we have. And finally, we compute the integral defining the asymptotics.